Good morning, everyone. My name is Renxuan Xie, a postdoc from UC Santa Barbara. I would like to first thank the organizers and session chair for this opportunity to share my most recent work. Today, my talk is focused on developing new super soft solvent-free elastomers that are compatible with more advanced processing methods needed in practical applications. At this AICHE annual virtual meeting, I've prepared two talks. One is on photo-crosslinker, the other is on 3D printing. So for this presentation, as the title suggested, it will focus on the 3D printing of super soft solvent-free elastomers. Bottlebrush polymer is known to form super soft solvent-free elastomer. But what is a bottlebrush polymer? Let's first start with the linear polymer network that we're all familiar with. In this case, each polymer is linked together by red crosslink points. Also, entanglements, represented by the green points, act as additional physical crosslinks. On the other hand, bottlebrush polymer, which has a backbone attached with unentangled side chains, they don't show any entanglements between crosslink points. Because of this property, Xie and co-workers were able to mimic biological materials such as jellyfish by engineering the bottlebrush architectures. Our previous work has also exploited this property for a capacitive pressure sensor. Because of the super low moduli, we're able to increase the sensitivity of the sensor by 53 times comparing with a linear analog. But how to make the bottlebrush network? Current approaches involve processing by simple and slow molding that dramatically limits their utility. As shown, a mixture of macromonomer, macrocrosslinker, and solvent is sandwiched between two plates and slowly reacted to form the swollen bottlebrush network by heat or UV exposure. So post-curing steps such as deswelling and drying are also required to form the dry network. Also, because the elastomer is formed directly from monomers, there's no direct comparison between the polymer and the final network. Therefore, the objective of our work is to first develop a new cross-linking process that is fast and solvent-free, and then use this approach as a stepping stone to achieve 3D printing. The cross-linking part is presented elsewhere in another talk on the AICHE virtual platform. So for this presentation instead, let's focus on developing the 3D printing capability of bottlebrush elastomers. 3D printing, as one of the well-known advanced processing methods, could enable new applications such as 3D printed actuators, sensors, or biomimetic materials. But as mentioned previously, developing new bottlebrush elastomers that are compatible with advanced processing pathways remains a challenge. So for the remaining part of the talk, I will first demonstrate the example of a such 3D printable super soft solvent-free elastomer. One of the simplest type of 3D printing is direct ink writing, which relies on the development of the yield stress fluid or sharp shear thinning fluid. By applying the stress above the yield stress, the ink material can transform from the solid to the liquid state and vice versa. Typically, the past approaches involve the addition of solvent, particles, or complex formulation to induce such behavior. But those approaches are not a viable option, as fewer particles would usually deteriorate the super soft mechanical property of bottlebrush elastomer by increasing its stiffness. Also, the evaporation of solvent can warp the printed parts during printing or drying. Instead, our approach is by leveraging the self-assembly of bottlebrush polymer to induce the yield stress fluid behavior without either solvent or particles. Then mixed with a small amount of previously demonstrated photo-crosslinker, the 3D printed soft solid can be transformed to a bottlebrush elastomer after UV curing. Specifically, the yield stress fluid property is achieved through the self-assembled body center cubic spheres, which is comprised of bottlebrush statistical polymer of polyethylene oxide and polydimethylsiloxane oxygen. PEO is the core, while the PDMS is a majority component. Therefore, the key design requirements for room temperature 3D printing of super soft elastomer is based on Bottlebrush statistical polymers with low TG sidechains. First, we will demonstrate that the Sachs profiles collected at room temperature does verify the expected Bragg reflection peaks for BCC morphology. And due to the unique self-assembly of Bottlebrush statistical polymer, the domain spacing is actually controlled by the sidechain length of PDMS as indicated by the Sachs as well. Additionally, the corresponding structure moduli, which is represented by the frequency-independent storage modulus, can be also related to the domain spacing measured by Sachs. For BCC morphology, it's expected that the G moduli scales with the domain spacing to the power of 3. Indeed, for these two samples with different sidechain length, the expected scaling is obeyed. Therefore, this relationship allows predicting the moduli of a self-assembled Bottlebrush statistical polymer. Then the yield stress behavior is characterized by the oscillatory amplitude sweep, where a sharp yielding transition is observed when the stress amplitude exceeds the yield stress value. The yield stress, which is located by the G' and 0' crossover, can be tuned by the sidechain length. Additionally, such yielding transition is shown to be highly reversible and quickly recoverable under multiple cycles of oscillatory shear across the yield stress. The yield stress behavior of the self-assembled Bottlebrush statistical polymer enables actually room temperature 3D printing. This is first demonstrated by 3D printing a self-supporting log pile structures with different grid sizes. Other printed objects such as a hollow pyramid and a helical extrudate are also shown. But in order to transform the printed soft solid to elastomer, a small amount of photo-crosslinker must be added to the formulation ink without affecting the yield stress fluid behavior. Here, we demonstrate the excellent 3D printability of the elastomer formulation ink by printing a bowl-shaped structure. This video is actually sped up by 100 times already, and the actual whole process takes about 40 minutes to complete. We also printed another bowl with a final resolution, as shown for the comparison, and also another dog bone specimen with a final resolution, so that we can compare the mechanical property between the printed part and the molded part later. The as-printed soft solid can be also transformed to the Bottlebrush elastomer after UV curing. The completion of the UV curing is not only indicated by the plateauing of a shear moduli, but also by tracking the rise and gradual decay of the fast fluorescence intensities. The video shows the entire UV curing process of the 3D printed bowl, which takes about 30 minutes to finish in real time. But here I have sped up the video for the convenience. In order to examine the mechanical property of a UV cured Bottlebrush statistical polymer, we first looked at a molded sample rather than a printed one. When plotting the engineering tensile stress versus extension ratio, the Bottlebrush elastomer undergoes the unique yielding transition when the yield stress is surpassed, thus dividing the tensile curve into the pre-yield response and the post-yield response. Additionally, such yielding transition is near perfectly recoverable as shown after multiple cycles across the yielding. Below the yield stress, we expect that the BCC lattice is only slightly distorted, while above the yield stress, the morphology of the stretched sample becomes disordered spheres. This mechanical disordering process is verified by the in situ tensile Sachs data, where you can see for the stretched sample, we lost the higher order reflection peaks. Now we're going to examine the mechanical property for both 3D printed and molded Bottlebrush elastomers by plotting the true stress versus extension ratio. Note that the print direction for the dog bone specimen is parallel to the tensile load. As shown, the pre-yield response is identical, and the 3D printed dog bone is weaker and less extensible than the molded one. The quantitative comparison in moduli is obtained by fitting the data with a classic rubber elasticity equation in the small extension region and with a vertically shifted Norberling model in the large extension region. As it turns out, the post-yield moduli, g of x, is essentially the same for both 3D printed and molded sample and has a value around 8 kilopascal. And this value is actually about 4 times smaller than that of the pre-yield moduli. Finally, we also demonstrate the good bonding between the printed layers of the bowl in this recorded video, where the tensile load is actually perpendicular to the print direction. In summary, hopefully I have conveyed that we have made some tremendous progress in improving the processability of Bottlebrush elastomers by designing a novel photo-crosslinker and a novel Bottlebrush statistical polymer. Specifically, we have leveraged the unique self-assembly of Bottlebrush statistical polymer into body-centered cubic morphology to induce the yield stress fluid behavior, which in turn allows room temperature 3D printing. Then, upon UV irradiation, the as-printed part can be transformed from a soft solid to a super soft, solvent-free elastomer with modulus of less than 10 kilopascal and with a near perfect recoverability above yielding. Finally, I would like to acknowledge Dr. Sandra Mukherjee for synthesizing the Bottlebrush polymers and photo-crosslinker mentioned in this talk, and would also like to thank Veronica Reynolds for helping me with the 3D printer. And of course, I would like to sincerely thank my both advisors, Professor Michael Chapnick and Professor Chris Bates, and both group members. I would like to also to acknowledge our funding source, Mitsubishi Chemical Center for Advanced Materials at UCSB. And I would like to finally thank you for your attention and looking forward to the live Q&A session. Thank you.